Howdy, welcome to Elementary Statistics. I am Lance Curtis. This is the lecture for Section 10.3, Prediction Intervals and Variation. Here in this lecture, we're going to talk about prediction intervals. They're in many respects like confidence intervals, but there's some important differences, and we'll get into that in this lecture. We'll also talk about the concept of standard error, explained and unexplained deviation, and how that relates to explained and unexplained variation. And we'll conclude with a look at what's called the coefficient of determination. So, in this section, we're going to present a method for constructing prediction intervals. Prediction intervals are very similar to confidence intervals, as I mentioned before. So, a prediction interval is like a confidence interval in that there's an upper and a lower limit, and there's an associated level of confidence. However, confidence intervals center around a population parameter. So before we were making confidence intervals, we said that the center of that interval between the upper and the lower bound was some population parameter, like a proportion, a mean, a standard deviation, what have you. Prediction intervals also have an upper and lower bound, but the center of that interval is not a population parameter. Instead, it's a single data point within the population. A very important difference, but that's what makes a prediction interval different from a confidence interval. So, when we're making prediction intervals, we're basically placing confidence level around a predicted value. So instead of saying that we're, for example, 95% confident that the mean of the population is within these two bounds, what we're saying with the prediction interval is that we're 95% confident that a given value that we're predicting with our mathematical equation, our statistical model, is within this upper and lower bound. So for each fixed value of x, there's a corresponding value of y. And we're going to assume that they're normally distributed about the regression line with the same variance. So if we have a fixed and known value of x naught, then the prediction interval for that associated y value is going to be given by this general form. So y hat minus e is the lower bound, y hat plus e is the upper bound, where y is the center of the prediction interval. Recall that y hat is what comes out of our regression equation, whereas y is what actually is the actual true value for y. That margin of error e we calculate according to this equation here. Notice that there's a term called S of e, which is the standard error, and that's given by a separate equation that you see at the bottom of the screen. Calculating this by hand is pretty intensive. We're going to use software to calculate our prediction intervals for us, but we will look a little bit at using the equations that you see here by hand, just so you can understand what the computer's doing. Note there's n minus 2 degrees of freedom with our standard error estimate. This is very important. So again, we see one more instance where there's n minus 2 degrees of freedom. Let's go back to our example of shoe print length and height. We previously found that there was a linear regression equation that described the relationship between these two variables. So, if we're given a shoe print length of 29 centimeters, the question we're asked is, what is the 95 prediction interval for height? So here we have our data that we had originally, and we have the regression equation that we found that provides the relationship between our two variables. The question is, what is the 95% prediction interval for the height? Well, first, we need to find the standard error S sub e, but to do that, we need the sum of the differences between actual and predicted values for y. So, going back to our original data set, we have our x values, which is the shoe print length in centimeters, and then we have the actual values for the height, which is Ry. These are the observed values. So these values, the y is going to form the center of our prediction interval. If I use my regression equation that was found previously, I can calculate a predicted value of y. This is y hat. So using each one of the x values, the shoe print lengths, I can calculate a corresponding value for y hat. And I can add that to my table here. Now I can subtract the observed value minus the predicted value. So take all the predicted values and subtract them from the actual value. So the first example here, I take 177.3 and I subtract it from 175.3, and that gives me -2. 177.8 minus 177.3 gives me 0.5, so on and so forth. So now I've got the differences between the actual observed values and the predicted values according to the regression equation. I can then take those differences and square each of them. So -2 becomes 4, 0.5 becomes 0.25, so on and so forth. If I add the squares together, I have the sum of the squares of the differences between the observed and predicted values. Adding all those numbers together in that row gives me 29.45. And now I have what I need to calculate my standard error. Notice we've just calculated what's in the top part of our fraction, the numerator. So I can substitute that value in. We have 10 samples, so n minus 2 is 10 minus 2, which comes out to 8. Punch this out on the calculator, and I get 1.919. Now I have my standard error estimate that I can use to calculate the margin of error I need for my prediction interval. Let's go ahead and calculate that margin of error. So here's our equation for margin of error. Notice we have everything that's called for in this equation except for our critical t value, t sub alpha over 2. I can easily find that value. Just go into my t calculator and StatCrunch, or alternatively I could use a t-table. I can find that value. Remember, n minus 2 degrees of freedom. So we want to put 8 degrees of freedom in here, not 9. And I'm asked to find 95% confidence. So that means that alpha is 5%. Remember, when you're using the between option for your calculator in StatCrunch, that you're calculating the area in between the tails. So we want to put 95% for that area. And then press compute, and out come my two critical values. I want to take the positive one for my margin of error calculation to 0.306. So now I have everything I need to calculate my margin of error. So I'm going to substitute all those values in, and you can see that here. I'm substituting all those values in, and then I punch this out on my calculator and I get 4.67 as my margin of error. Now I have what I need to calculate my prediction interval. I just substitute into the general form. So here's the general form. Notice that the y hat I get by putting in the x value they give me in the problem into my regression equation. That came out to 176.28. My margin of error 4.67, so I subtract on the left, add on the right, and out comes my prediction interval 171.61 to 180.95. What this means is that we're 95% confident that the true height of someone with that given shoe print length is between 171.61 and 180.95 centimeters. Well, that's a pretty large range of values when you're talking about height. So a single shoe print length isn't really telling us all that much about a person's height, because the width of our prediction interval is pretty wide. Let's use this same data set to explore the concept of explained and unexplained deviation. So here we have a scatter plot all 10 of our data points, as you see here. We also have our regression line, and we also have the mean value line. So for any given regression, we have two possible choices when we're making predictions. Okay, either our regression model is going to be good enough for making predictions, in which case we can use that model. So we have the slanted red line that you see here. Here's our equation for that line. Y hat equals 128.91 plus 1.63x. If the regression model isn't good enough to be used for making predictions, we can use the mean value. And so that's the horizontal line that you see in the center of the scatter plot. Y bar equals 177.22. This is the mean value for the Y values of our data set. So we're going to use one of these two lines to make predictions, depending upon how fit the regression model is for making predictions. Now, notice that each of the data points deviates from both of these lines. So some data points have large amounts of deviation, and some data points have small amounts of deviation. In other words, some data points are farther away from those lines than are others. Let's look at this data point up here at the top, for example. So x value of 30.6, y value of 181.6. Let's take a look at this data point and examine its deviation. The explained deviation is the distance between the regression line and the mean. So this distance we can actually explain because we know where it comes from. We know what the model is. We know how we derived it. We know what the mean value is and how we derived it. So the difference between these two beneath this data point is the explained deviation. We know where it comes from. There's another difference, which is the unexplained deviation. This is the difference between the data point and the regression line. So here we have deviation that's unexplained. We don't know where it comes from. We don't know why we're deviating as much as we are from our prediction. We don't know what bridges the gap between what we're observing and what we're predicting. And so that's why this portion is called the unexplained deviation. Notice in both cases we're looking simply at the vertical distance between data point, regression line, and the mean value line. If we add the explained and the unexplained deviation together, we get the total deviation. And this makes sense, right? Either something is explained or it's not explained. There's no middle ground there. So if we take everything that's explained and add it with everything that's unexplained, we get everything there could be. That's the total. So total deviation is simply the distance between the data point and the mean. This is everything. The unexplained, which is the distance between the data point and the regression line, and the explained, which is the distance between the regression line and the mean value. Let's take a look at another data point. Look over the lower left-hand corner of the scatter plot. X value of 28.4, Y value of 174. Our explained deviation will be the distance between the mean and the regression line. The unexplained deviation will be the distance between the regression line and the data point. Again, we're looking at vertical distances here. So only the Y values are considered, not the X. Total deviation is the distance from the regression line to the data point, from the mean line to the data point. In other words, we're adding together the explained and the unexplained deviation. Let's take a look at some of the numbers involved with deviation. Actually running through these calculations. So now we've covered the concepts. Let's actually put those concepts to work with the math and do some calculation. Again, looking at this first data point that we looked at earlier. So if we go directly below the point on the regression line that has the same X value is shown here. So its y value is 178.2. And the equivalent value on the mean line, in other words, it has the same x value, its y value is going to be 177.22. So now we can do the same thing with the second data point that we saw earlier. So its corresponding point on the regression line is shown here. Corresponding point on the mean line is shown here. So now I've got all the values I need to calculate the differences for my deviation. So remember, explained deviation is the distance between the regression line and the mean. So for the first data point, that's going to give me 0.98. I take the y value for my predicted, which is the regression line. I subtract out the mean. So 178.2 minus 177.22 gives me 0.98. Alternatively, for the second point that we looked at, explained deviation is going to be 175.31 minus 177.22. This gives us an explained deviation of negative 1.91. All the difference here that we see between positive and negative deviation, remember, positive deviation means your data point is above the regression line. Negative means it's below the regression line. Now we've got unexplained deviation. Let's calculate the unexplained deviation. So unexplained deviation is the distance between the data point and the regression line. So for the first data point, we're going to have a deviation, it's unexplained, of 3.4. So I'm going to take the data point 181.6, subtract 178.2, that gives me 3.4. Likewise, for the second data point, I take its y value and subtract out the predicted value, and I get negative 1.31. Total deviation is in the distance between the data point and the mean. So here I can follow one of two paths. I can either take the data point and subtract the mean, or I can add the explained and the unexplained deviation together. Let's look at it where we actually do the total distance. So the data point for the first data point, our y value is 181.6. I subtract out 177.22. That gives me a total deviation of 4.38. Likewise, for the second data point, I have a total deviation of negative 3.22. Again, positive deviation means our data point is above the regression line. Negative means it's below. Notice I could have just added the explained and the unexplained deviation together. So for the first data point, 0.98 and 3.4, if I add those two together, I get negative. Oh, wow, looks like there's an error there in my little note. So if I take 0.98 and add to 3.4, I'm going to get 4.38. Likewise, negative 1.91 added to a negative 1.31 gives me a negative 3.22. So they're not necessarily equal to each other, but I can add together the explained and the unexplained to get the total. This leads us to the concept of explained and unexplained variation. So as we just saw, total deviation is the sum of explained deviation and unexplained deviation. We can write that mathematically as follows. So total deviation is going to be the distance from our data point to the mean line. Explained deviation is the distance from the regression line to the mean line, and unexplained deviation is the distance from the data point to the regression line. Notice if I add these two quantities together, I get y minus y bar, because here I got y hat minus y hat, so that goes away, and I'm left with a negative y bar and a positive y added together, which is y minus y bar. So we can say that this is actually synonymous to the sum of the squares. It's not exactly mathematically equivalent, but it is similar enough to where we can make the jump and say, okay, we can actually transform our y minus y bar to the sum of the squares of y minus y bar. This represents the total variation in our data set, or rather the total variation in our regression model. I can do the same thing with the term for explained deviation, and I get the actual term for explained variation. Likewise, for unexplained deviation, I can perform the same operation and get the term for unexplained variation. I then find that I have the same relationship between my variation terms as I do between my deviation terms. So if I add the explained and the unexplained, I get the total. So now we have made the jump from deviation to variation. And these variation terms are going to be useful for determining the fitness of our regression model. The way we're going to do that is by using a quantity known as the coefficient of determination. We've learned earlier that the coefficient of determination is the amount of variation in y explained by the regression line. So when you think about this definition, what's really being communicated here is this amount of the variation in y is like a portion, meaning it's a portion of the whole, which makes it a proportion or a fraction. So we can actually define this by writing it out in terms of a fraction. The amount of variation explained by the regression line is the explained variation divided by the total variation. We have the part over the whole. This is our proportion. We can actually, using the mathematical terminology that we encountered on the previous slide, substitute in for the words, and we get a mathematical representation that will give us a number that we can use for our coefficient of determination. As it turns out, this value is the same as our linear coefficient of correlation squared. So R squared is the coefficient of determination. This is the amount of the variation in y explained by the regression line. Now, the value of R squared is the proportion of the variation in y explained by the linear relationship between x and y. This is just translating that general definition of coefficient of determination and applying it specifically to the regression model for a linear model. Let's look at our regression equation for shoe print length and height. So we were given we developed a linear correlation coefficient from our model of 0.847. So that means our coefficient of determination is simply 0.847 squared, which is 0.717. This means 71.7% of the variation in height, which is our y variable, is explained by the linear relationship between shoe print length and height, our x and y variables. The remaining 28.3% of the variation is unexplained. We can't account for that. We don't know why there's such a difference between the predicted value and the observed value. Let's look at an example problem we've seen before. Cereal killers. The amount of sugar in cereal. If you get too much sugar, you will die. Actually, excess sugar consumption is linked with a host of health problems. I read an interesting article the other day that talked about how the sugar industry back in the 60s was funding a bunch of studies to influence the common thought about sugar consumption. Not really surprising, since they stand to make a lot of money depending upon the way that people were thinking about sugar consumption. Anywho, we have 16 different cereals, and we we recorded the grams of sugar per gram of cereal, and also the calories in each gram of cereal. And we were looking for a linear correlation between the two. We found that there was a linear correlation coefficient of 0.149. We have the regression equation where x represents the amount of sugar. We're told the mean of the 16 amounts of sugar, so this is x bar, 0.295 grams, and the mean for the calorie counts, this is y bar, is 3.76. Now we're asked to answer the following questions. First question, what is the coefficient of determination? Second question, what percentage of the total variation in the number of calories can be explained by the linear relationship between the amount of sugar and the number of calories? Let's take a look at this. So the first question is, what is the coefficient of determination? Well, if you wanted to, you could go back and redo your analysis, but you don't have to. You were given a value for R, your linear correlation coefficient. So to get the coefficient of determination, all you have to do is square it. So we just take our value for R and we square it, because R squared is the coefficient of determination. 0.149 squared, 0.022201. We can round that to as many decimal places as we're asked. Second question, what percentage of the total variation in the number of calories can be explained by the linear correlation between the amount of sugar and the number of calories? Well, that's just asking for R squared in percent form rather than in decimal form. So I take my 0.022201 and turn it into a percent. I get 2.2201%. And again, I can round that to as many decimal places as I'm asked. So that's all there is to it. I don't have to redo any analysis. I just take the R value that's given to me and I can square it to get my coefficient of determination, turn that into a percentage, and that percentage is the total is that portion of total variation that's explained by the linear correlation between my x and y values. Let's look at another example problem. We've seen this one before, lemons and car crashes. So here we have the same data set that we have seen previously, but we have new questions. First, what is the coefficient of determination? Second, what percentage of the total variation in car crashes can be explained by the linear relationship between the weight of imported lemons and car crash fatalities? And three, what is the 95% prediction interval for car crash fatalities given 300 metric tons of imported lemons? So first question, what is the coefficient of determination? Well, I can go, if I don't actually have the R value handy, it's not that hard a matter to actually redo the analysis. Inside StatCrunch, go to Stat, Regression, Simple Linear, indicate your daily columns, press Compute, and then when you get your results out, you can do one of two things. You can either take the R value and square it, or you can just look at the line below and see your R squared, it's squared that value already for you as R squared. So you can just take that right off the results window. So if you want to double check, you can always take your R value and square it, but you'll get the same number. Second question, what percentage of the total variation in car crashes can be explained by the linear relationship between the weight of imported lemons and car crash fatalities? Well, here, we just take R squared and we express it as a percent, not a decimal. So you move that decimal point over 2 places to the right, and that gives us 91.96%. There's the answer to the second question. Our last question is asking about the 95% prediction interval for car crash fatalities given 300 metric tons of imported lemons. So remember, lemon imports is our X, crash fatalities are the Y. So we're given an X value and asked to make a 95% prediction interval for the corresponding Y value. We're going to use StatCrunch to do this. So if you go back to the options window, there for your simple linear regression, and notice down towards the bottom, there's an area labeled prediction of Y. So here you're actually going to put in the value for X that they give you, which in this case is 300. And there's a level, a confidence level surrounding the prediction. So I'm going to put in 95% because that's what the problem asked us for. Once I put these values in, I press compute. Out pops my results window. And notice there's an extra table there at the bottom of my results window underneath the ANOVA table. So here I actually have my 95% prediction interval right there at the end of the table. And there's my 95% prediction interval. So no need to go through all that intensive calculation that we saw earlier. It's much simpler just to use technology. Very thankfully, we live in the 21st century. And that brings us to the end of this lecture. If you have any questions, you know what to do. Otherwise, I will see you in class or the next video. Thanks for watching.